The focus of this work is autonomous driving, off-road autonomous driving in challenging environments. Here we see our vehicle decided to leave the road to navigate to a waypoint around the marker 4 in the map. This work was done as a collaboration with JPL and through the support of the DARPA Racer project. We are motivated by the need for continuous speed adaptation as a function of the environment. Our task is to drive as fast as possible to a GPS waypoint with no prior mapping and only onboard sensing capabilities. This means our vehicle will need to choose an appropriate path and speed for that path on a wide range of inputs without being overly conservative. Our visualization is running in real time and shows the 4 camera arrays and the visualization of the mapping pipeline and planned trajectory. The colors of the cost map denote different concepts of traversability. Purple shows unknown space. This can be thought of as places where the traversability is uncertain and the vehicle should not enter it. Hazards are shown in a gradient from yellow to red, with black denoting lethal obstacles and gray being traversable. Trails are semantically detected and marked in light blue. The red to blue line emanating from the vehicle indicates the desired trajectory from our approach, and the green ellipses show a propagated expected Gaussian distribution for the dynamics. The vehicle's speed is shown in the top left of the map in meters per second, and the speed is artificially capped to 12 meters per second. We are showing clips from a 3.3 kilometer traverse that includes rapid environmental changes like going from roads to open fields with substantial elevation changes, or dense vegetation that we might need to drive through. We note that our perception is varying rapidly, so the pausing of the planning stack at certain moments is likely due to the noisy perception that can occur when looking at difficult traversability decisions. A core component of the planning stack highlighted in this work is the distributional dynamics and their use with the MPPI trajectory optimizer. We learned the distributional dynamics using a combination of principled physics-based models and 2 small LSTM neural networks. Our dynamics model a Gaussian distribution and rely on the linearization of the parametric dynamics to propagate that distribution. One neural network improves the mean fit by compensating for errors of the parametric model additively in the force space. The second learns the process noise using a hybrid structure. The uncertainty grows with speed, so that is the main signal used on the vehicle to determine what speed to go. If a large uncertainty is possible, then the vehicle will go quickly. If a small uncertainty is needed, the vehicle will naturally slow down. This also generalizes well to disturbances, since those can increase the size or change the shape of the uncertainty. We also know that the shape of the uncertainty is key and depends on the parametric equations. We fit an open loop uncertainty from the data and used hand-tuned feedback gains to reduce the uncertainty in the propagation to better approximate the closed-loop behavior of the vehicle when it is run as a receding horizon planner. The trajectory optimizer uses the predicted Gaussian distribution when rolling out the dynamics to cost trajectories by computing the CVAR over the empirical distribution generated using the unscented transform. The distribution is a 4D Gaussian over x, y, yaw, and forward velocity. In order to generalize, we found that relying on the uncertainty to control speed outperformed other environmentally dependent hand-tuned rules. In order to properly encode the relevant constraints and objectives, we relied on principal approximations of human understandable things like suspension force, acceleration, and collision with the cost map. We found that the distributional approach gave speed adaptation that seemed intelligent and anecdotally approximated human driving. Our approach was able to handle a large dynamical disturbance like is shown in the first case study. The vehicle is sliding on the rocky creek bed and goes slow due to the elevation hazards and a fallen tree that is semantically detected as a hazard, but late and with delay. Next, the vehicle will enter a muddy field and have a high-speed slide. Pay close attention to the distribution, shape, and size as we start this slide. We can see that the distribution grows to accommodate for the high initial lateral velocity, and the vehicle does not hit any obstacles, even under these large disturbances, due to the uncertainty size and shape. Our vehicle continues to apply throttle through the entire slide since it is not near hitting an obstacle. Also, the uncertainty shrinks back to normal size after the vehicle returns to solid ground. We do not penalize directly on the shape or size of the uncertainty, except how it may impact the cost function with respect to the environment. The second case study shows navigation of a tight slope. Watch for the planner to match the size and shape of the uncertainty to the navigable area of the slope. The left-hand side is constrained by the lethal hazards of the tree, and the right is constrained by the ditch immediately to the right and the possibility of rolling over into it. Again, the size and shape of the uncertainty is influenced by the terrain. Increasing the lateral size due to the high roll angle ensures the vehicle provides sufficient space away from either hazard under the uncertain dynamics. Since this uncertainty is state dependent, it can adapt to what's going on in the environment, and that leads to good generalization. Finally, we show the impact of altering a scaling factor on the uncertainty size. This can be thought of as changing the probability of constraint satisfaction we would like. The left shows a C sigma of 1.0, and the right shows one of 2.0. All prior results are shown with a value of 2. Here on the tighter trail, we can see that the vehicle on the left screen is limited by the width of the trail, meaning that the vehicle will drive slower in these sections. On the right-hand side of the screen, we see that the uncertainty is smaller, so it is not limited by the width, but more the length. This is the main reason the vehicles drive differently in these two scenarios. This is entirely dependent on the environment. In this second clip, we see that the vehicle drives a similar speed independent of the C sigma tuning parameter because the trail is wide enough. Our speed was limited earlier based on the environment, but in an area where it is sufficiently safe, we will drive fast as well. We thank the JPO and DARPA Racer team for the opportunity to work on this exciting project.